But why are you sharing your this thing? Your cover pic?
Okay. Okay, you got it? Ruben, your hand is raised.
It's 62.80.
52.8 meters. Okay. Yeah, so we're all getting the same answers now. Yeah. So in examination, I can ask you to do the proof for me, and I can give you questions that define the range or the time to maximum height, or I can put it in another form for you, okay? So you take note of that. Okay, so moving on, please inform your colleagues.
So
Inform them that we are still in class.
okay.
Now let's move on. So that ends.
Sir.
Yeah.
Sir, please, in examination, or can you ask a question like this? Maybe you can give us the this thing, the T maximum and this thing, the velocity, the V naught, whereby you won't give us the this thing,
the angle.
The angle.
Yes.
Can
So
you be asking a question like that? Yes.
Yes, I can do that.
Oh, okay. Okay.
Okay, somebody is asking for the height. So anybody who has it, you give it to the person. Or you wait after the video is posted, then you look at the calculation we had. Yeah, now we want to move into dynamics. Okay. In dynamics, like we said from day one, dynamics deals with what? Forces and their effects, okay, on motion. Okay. So the effects that forces have on what? On motion. Very good. And there are very important laws which help us to what? Analyze the effect of forces on motion. Okay. And these laws are the Newton's laws of motion, which a lot of us are already aware of. Okay. So we'll be looking at them again. We have three laws, which is the first Newton's first law of motion, second law of motion, third law of motion. Okay, the first law of motion we know is for an object to continue in a state of rest or in uniform motion, okay, then it's, or for it to this thing, then there should be no external force. But if a body, okay, continues in a state of rest or uniform motion, unless compelled by what? To change that state by what? An external force. So in other words, in the presence of an external force, the body will cease to be in a state of rest or what? In a state, in a uniform motion. Okay, good. So this essentially talks about what? Forces. Okay, forces acting upon what? Objects, or introducing the concept of friction as well. Now, so I've mentioned that. Then the next point is Newton's second law says that if a net force acts on a body, it will cause an acceleration of that object. Okay, if a net force acts on a system, then it will cause an acceleration of the system. So for example, if I have a plane like this, and I have an object like that, okay, and we have one force which is causing this body to move down, okay, we have another force which is drawing this body to this side, okay, and then possibly the frictional force going, let me represent that with another color, okay, depending on the motion of the body, we could have the frictional force also what in play. So at the end of the day, we are going to have, let's say, force 1, force 2, okay, and then force what 3, which is the frictional force, okay, good. And then what we are saying here is the net force acting on the system, okay, the net force acting on the system will cause what, an acceleration of the system, okay. So the sum of all forces in the system, okay, is proportional to the acceleration of the system, okay. And then if you put it that way, then that is going to be, if you want to write that in another way using the constant of proportionality, that will be equals to ma, okay. So if in the case where all the forces balance out, then we're going to have a state of equilibrium. Equilibrium means the system will not be moving, right? And once it's not moving, there is no speed, which means acceleration will be what? 0, okay? So in a state of equilibrium, then the sum of all forces is going to be equal to what? Is going to be m times 0, which will be equal to 0, okay? So you take note of that. Okay, then moving on, we talk about the third law, which is for every action, there is an equal and opposite what? Reaction. Okay, that too we know. Okay, now let's look at some few forces. Since we are dealing with forces, we have to know how the forces act and in what direction. The first force is mass. And the first clarification we want to do is the difference between mass and weight. Okay, now weight is a vector quantity, and the weight of an object, okay, he said, let me read what we have here first. He says mass is the measure of the amount of matter in an object. So the amount of matter in a pen will not change because that is the makeup of the pen. So if you even take the pen to the moon, the pen will still remain as what? A pen. But when it comes to the weight, because the weight of the object is influenced by the gravitational force, okay, the weight of the pen on Earth will be different from the weight on the moon, okay, good. Then again, because weight is a vector quantity, the direction of weight always acts where? Downwards, okay, acts downwards, okay, in the direction of the acceleration due to gravity. Then we also have what we call as the normal reaction, okay, and the tensional forces. I'm going to squeeze this a bit, okay, so that I can draw some diagrams. So let me put this here. Good. So when it comes to normal reaction, we are saying that the normal reaction is the force is perpendicular to the interface on which an object touches. So if there is a table like this, let me get my table correct, and I have an object sitting on this table, okay, then the weight of this object, which will act from the center of mass, okay, we know weight will always be down, okay, that's W. Now there is also another force which is exerted by the surface, okay, of contact. There is a force exerted by the surface of contact, which we call as the normal reaction force, okay? And that force always acts at what? Perpendicular to the surface. Perpendicular means 90 degrees, okay, to the surface of what? Contact. So that is the normal reaction here. So in other words, if the surface of contact changes, okay, if the surface of contacts, then let me mention this whilst we are moving on. So in this scenario, we have y, and then we have what? X, sorry, negative y, and then we have what? Positive x and negative x, okay? Now, if the surface changes, let's say the surface has now changed here, okay? Good. We'll have, if the object touches the surface this way, right? Good. Your weight of the object always acts perpendicularly down. It will always act, vertically what? Down, okay? Weight will always act vertically down. But your normal reaction always acts perpendicular to the contact surface. So take note of that. For normal reaction, you always look at what? The contact surface. This is the surface of the object. Then you look for your 90 degrees. Okay, so it's always going to go that way. So this will be your normal reaction. Okay. Then again, let me make mention of this. So here, because the plane has changed, this is now your x. This will be your y, your positive y. Okay. This will be your positive x, and then this will be your negative x. Okay, and negative y. Okay. So in further analysis, this is how you're going to do your interpretation. The moment the surface is inclined, okay, your coordinates will also change briefly to suit that. Meaning this has now become the horizontal, okay? Very good. So in other words, your normal reaction, okay, is not always equal to your weight. Or let me put it this way, your weight is not always equal to your normal reaction. You take note of that. Then the next thing is tension. Okay, so tension, as for tension, I think we've seen it several times. He says whenever we use a rope or anything like a string, okay, to exert a force on an object, we are creating tension in the rope that transmits the force we exert on the rope to the object and to the other end of the rope, okay? So anything, for example, when you put a school bag at your back, that there is tension, okay, in the handles. When you are using a rope to pull a bucket of water, there is tension generated in what? In the rope, okay? And that tension is what is going to cause the resultant acceleration of the system. Okay, then we have push and a pull, okay? So that too, I think we are very okay with that. But let me just touch on it. Anytime we are talking about a push, you see the direction of motion is to the object, okay? Whereas for a pull will be what? Away from the object. So this is a pull, this is a pull, this is a what? A push. Okay, good. So we have a pull and then we have a push. Now, moving on, we have some applications here, okay, in force diagrams. So when we talk about force diagrams, here we are talking about representing only the forces acting in a system. So if it's a tension force like we have in this scenario, you indicate that the tensions, okay? So this is a rope, this is also another rope, and this is a third rope. So this weight is causing a tension here, okay? And then there is a tension here because this body is attached, okay, up here, okay? And then there's also a tension generated in the other side of the rope, okay? So we're going to have the corresponding force diagram will be what? T1, T2, and then what? T3, okay? Very good. So let's move on and take some examples. Our time is really running quick. So we move to the next example. It says, considering the diagram below, we are supposed to find the magnitude of the tensions T1 and T2, okay? And we've been given the weight of this object, which is T3. T3 is as a result of this mass over here. Okay, good. So let me move the diagram a bit. Then we run the force diagram and run our analysis subsequently. Okay. So looking at these forces here, clearly we can see that if we should draw the, okay, let me put it this way. My diagram is not too good. Let me try again. Okay, so we draw a horizontal line here. Okay, then clearly this tells us that these vectors can be resolved. Okay, good. So let's do it this way. So because this tension is acting up, this other tension is acting up, and then this other tension too is acting down. Okay, we'll first have to, we'll use our first okay, mode to split them into x and then y components. Okay, and then resolve the individual vectors. So which means alternatively we can be moving to the right and then to the top here. Okay, for the first vector, this will be T2. This will be T2 what? T2, Then the angle here, because we have a Z angle, okay? This is a Z angle here, right? This is a Z angle. So this angle to be what? 20 degrees, okay? The same way to this will also be Z angle. So the angle here will also be what? 60 degrees. So we take note of that. Okay, so we have 20 degrees here. Okay, so this will be T2 cos 20, and then this side will be T2 sine of 20. Then when it comes here, this will also be, so you take into consideration the directions. Okay, this will be negative T1 cos what? 60. Okay, T1 cos 60, and then this will be positive because we are going up. So positive T1 sine of what? Sine 60. Okay. Okay, so let me write the two first. So for this one, we have T2 cos 20. Then we have T2 sine of 20. Then for the next component, we have T1, negative T1 cos of what? Cos of 60. And then we have T1 sine of what? Sine of 60. Then we have then for the last one, that is the weight. Okay, so let me clear this side. So the weight is acting vertically downward. There is no x component to it. Okay, so we can write that to be what? The x component is 0. The y component is going to be the weight. Weight, we know weight is what? M times G. Okay, that will be M G. Okay, we know M is 5. So whilst I'm writing the equations, you also have to be finding the sine 20, the cos 60, and those things for me. Okay, we have to rewrite it again. Okay, so what we do here is to apply Newton's second law of motion. Okay. The second law of motion says that the net force acting on the system, okay, will cause an acceleration on the system. However, we know that this system is in equilibrium. And because the system is in equilibrium, then acceleration is equal to what? Is equal to 0. So in other words, the net force on the system, okay, will be equal to what? 0. So then we can write two equations. In other words, the net force in the x direction will be equal to 0. And then the net force in the y direction, okay, will also be equal to what? Will also be equal to 0. So in other words, if we are going to add all the forces in the x components, we'll get this equation. So let me move this a bit. So we're going to get okay. Somebody is asking, why is the force? You thought the force is equal to 5k. Kg is mass, it's not force. Okay. So take note of that. Force is in newtons, not in kilograms. Okay, so moving on, we have let's write the equation. So the net force in the x direction will be T2. Have you found the cos 20 and the sine this thing for me so that I write it straight away? Cos 20, what did you get? Cos
94.
Please come again.
0.94.
Okay, so 0.94 T2. Okay, minus cos 60. Cos 60. Cos 60.
0.5.
So 0.5 T1. Okay, these are the two forces there. Okay, should be equal to what? 0 per the Newton's second law of motion here. Okay. Then we do same for the y component. That will be T2 sine 20. So give me the sine 20 first.
0.34.
So we have 0.34, 0.34, okay, T2, then sine 60,
0.87.
0.87, T1, okay, then plus the weight is what? Again, the weight is acting downward, okay? The weight is acting downward, so it's supposed to be what? Negative, okay? So don't forget to add a negative there. So this will not be plus, this will be negative, okay? Because weight acts where? Downwards, okay? So this will be minus what? The mass has been provided as what? 5 kg, and acceleration due to gravity, G, has also been provided. But let me write G here for the meantime. So this will also be equal to what? 0, okay? So if we are to rewrite these equations, this will be G is 10. If we are using G to be 10, then it will be, this side will be what? 5 times 10, okay? 5 times 10. Please follow carefully. So 5, the mass is 5, G is 10. So that will be 50, okay? So I'm going to change that and write 50 over there. So this will be 50. So 50 is equals to what? 0. Yeah, then you solve these two equations simultaneously. So do that whilst I address the chat. I've seen some comments in the chat box. So let me address them. Okay, I think Eric has understood. Okay, that's fine. So we're okay. So now we have to solve this simultaneously. Okay, you have to solve this simultaneously. You can make T1 the subject in the first equation. So which means that it's going to be what? T1 is equals to what? 0.94 T2. Okay, 0.94 T2. Okay, over 0. What? Over 0.5. Okay. So T1 is equals to 0.94 T2 over 0.5. Then you come and substitute into the second equation, okay, to find your T2. So find that for me. Our time is almost up. So I think I'll ask you to find this one at home for me. I have another class immediately after this class, okay? So we'll wrap up on our class. Just find T1 and T2 for me. And maybe you can do that before we wrap up for today. So T2, somebody has 38.59 newtons. And then T1 will be yeah, so T1 is 72.6 Newton. Okay, so that is it for this application here. Next week we'll be diving deeper into kinematics in 2 dimensions, especially on dynamics. Okay, so read the notes. You have the notes I used today. I think I've sent it to you like 2 weeks now. So just read through the notes and you'll be fine. Okay, so wrapping up on today's class, I've seen 2 questions. You let me take them. So first hand, what the hands? Yeah, so let me take the first. Michael, your question.
Okay. Hello, sir.
Yeah, I'm listening.
Good evening, sir.
Yeah, evening.
So my question is about the assignment you gave us on